So last time we derived the equation motion up to second order in time derivative of this density operator rho diagonal of Q by Heisenberg equation motion, and we could show approximately that this second order Heisenberg equation motion indeed can lead to the desired form of this density oscillation or plasma oscillation on the right hand side of the equation, where it is given by h bar square omega square, where omega is called plasma oscillation frequency, omega p, and times the rho diagonal of Q. Okay? And we show that this term leads to two subterms. The first term is the kinetic energy term, which is high order in Q. When Q goes to 0, this is at least order of Q squared. So this term is negligible, and so we cross out this contribution from the first term, and we generalize the second term, which looks horrible, but we know very well that this term can only lead to some number operator or occupation number or a density operator. Okay, so if we cannot combine this operator in such a way that we get such a Fermi function like this occupation number operator or the density operator, then we don't think they will contribute. Okay, so let's do it. So you can see that at the end of the last lecture, I pointed out that there are only, say, two possibilities. One is when Q is the same as Q prime, and the other is when Q prime is minus Q. So in other words, you could form this C dagger PCP, this number operator, if Q is the same as Q prime. So this vanishes. So this momentum indices on the C dagger operator is the same as C, and C dagger PCP is the number operator. If you take the expectation value of the number operator, this is precisely the Fermi function. Okay, so everything's about the Fermi function. So if you can form a Fermi function, and we're done. Okay, so we neglect all the terms that we cannot form occupation number or density operator. Okay, because that contributions are either 0 or negligible. So that's the key. So let's just do the algebra by considering these two subcases that Q prime is the same as Q or minus Q. So let's discuss the first case where Q prime is the same as Q. So you simply just plug in this condition in the bracket, and let me just write down what we have. Sum over P and this, and C dagger P, CP minus Q rho Q and plus rho Q, P plus 2Q minus P plus Q, and C P minus Q. So when Q prime is the same as Q, and you could immediately see that you get something like number operator here, and also C dagger P plus Q, CP plus Q, because both operators have the same momentum indices. Okay, but then you could redefine this moment indices by shifting this P by, say, minus Q, so that this P plus Q is the same as, say, P prime, and so on and so forth. But first term, you simply just use this number operator, N of P, and this is N P plus Q, right? Okay, but don't forget there's a summation over P in the very beginning of this form, and the momentum need to be summed. Also appear on the left hand side of this bracket with this P dot Q. Okay, so the summation over P involves every term. Okay, here and there. And therefore, but we need to separate these cases. So, and this term is, the first term is what? This sum over P dot Q and V of Q. So I forget about this constant prefactor. So this is MP, right? Minus NP plus Q, right? okay? Of course, times rho dagger of Q. But then you could, as I mentioned, you could shift this the indices of the second occupation number operator, so that this, I would change this momentum P in front from P to P minus Q, okay? And then you could take the difference between these two terms, okay? And this is given by P dot Q, C dagger P, CP, minus P minus Q, dotted Q, C dagger P, CP, which is Q squared, C dagger P, CP. Of course, you need to divide this by volume. All right, so you cannot simply just cancel this because these indices are different, right? This is MP, this is MP plus Q. But you could actually shift this indices as I mentioned. So P goes to P minus Q, and therefore P plus Q becomes P plus Q minus Q, which is exactly the same as P, right? But the price to pay is this momentum P will get also shifted from P to P minus Q, all right? Okay, so that these two terms will not get canceled. Instead, this is the same prefactor, this number operator here and here, but the first term P dot Q, the second is P minus Q dot Q. Okay, so P dot Q get canceled, so you left with only this Q square minus minus plus. Okay, so I skip all these details. So this, let me just use term A and term B. So term A is going to be Q square H bar square and 1/2 of V of Q and rho 0, rho dagger Q. So remember, as I mentioned, if you sum over P C dagger PCP divided by the volume, this is what? This is exactly rho 0, right? So this is rho 0. Okay, so we defined this many times in the past, so you should recognize that. Okay, and this is advantage because when we convert all these complicated operators in terms of the number operators, and we immediately recognize this form that we already defined. For example, if you sum over all this occupation as function of momentum P, and what you really do is to get the average density, right? Rho 0 is precisely the same as average density. But you also need to multiply this by rho dagger of Q at the end. So at the end of the day, this is rho 0, rho dagger of Q, and of course this Q squared comes from difference between these two terms. The P dot Q term get cancelled. Very simple. So let's look at this term B. As I mentioned, this B contains this operator C dagger P plus 2 to Q and CP. So can this C dagger C be converted into some number operator? No, there's no way. Because if Q is 0, and of course, but we are not talking about Q0 case. For any finite Q, this moment indices appearing in the C dagger and C are different. So by no means can we make them number operator. So let's look at the second operator. So C dagger P plus Q is CP minus Q. Again, for the same reason, for any, say, finite Q, non-zero Q, these two operators cannot be carrying the same moment indices. And therefore, this operator, C dagger C with a different moment indices, cannot be converted into any number operator. So 0 and 0. Why? Because if you look at this C dagger P1 and CP2, okay, and whatever this Dirac, say, Broglie cascade that you put here, this will give you 0 at the end. Why? Because this tells you that you destroy electron at momentum p2, right? But you create electron at p1. So that, the state p1 and p2 are orthogonal for one thing. Another thing, that this number of electrons carry the same momentum is gone. Okay? So you have one electron less carrying momentum p2, but you get one more electron carrying momentum p1, but p1 is the same as p2. Okay? And therefore, this is by orthogonal normalization condition, this is exactly 0. Whatever states that you insert, it doesn't matter. Okay? And likewise, this operator, when you evaluate this expression value, of course, you need to sum over p and q, but I don't care, because as long as they don't carry the same momentum indices, they definitely will vanish, because of the same reason that you will get the end of the day, the states, the Dirac-Broglie and the Cat state, which are orthogonal to each other. So these terms are all 0, so you get nothing. So that's really easy. And so you summarize this first term, which is just the contribution from A. So there's no contribution from B. And so similarly, so you could calculate the second case when Q prime is minus Q over here. So you could follow the same derivation, and you can show that this is given by what? The same result. Okay, so both term 1 and term 2 turn out to be the same, and you simply just add them up, and therefore the second term is what? The contribution from term 1 and term 2 give you the second term is actually 2 times term 1 or 2 times term 2, because term 1 and term 2 have the same value, so you get a factor of 2. So this is h bar square q square over m v of q rho 0 rho deg of q. Okay, so we're almost done. So the second order Heisenberg equation motion now becomes what? This term number 2. So let me just write it down one more time. So this is h bar square 4 pi e square m rho 0 rho deg of q. Right, so this is double commutator. And this is h bar square omega p square rho deg of q. We're done. Okay, so let's look at this contribution from term 2. You get q squared times v of q, right? So v of q is the unscrewing Coulomb potential in momentum space, which is 4 pi e squared over q squared. Okay, so q squared times v of q, and you immediately see that this q squared get cancelled, because it's factor of q squared in the numerator and one factor of q squared in the denominator. So this q squared cancel with that q squared in the denominator, so there's no q squared dependence. Okay, so that's really beautiful, because this is indeed a constant. Okay, so which is made of h bar and 4 pi e squared h bar squared and divided by m times rho 0. And rho 0, you know that this is nothing but the average density, okay, which is also the constant, the volume density. So this is the number densities. It's the number of electrons per unit volume, which is also constant. And we're done. So we are successfully derive such a plasma oscillation frequency. So omega p, you could read off from this by comparing this left-hand side to right-hand side of the equation. Omega p squared 4 pi e squared rho 0 divided by m. And omega p is known as the plasma oscillation frequency. And different materials shows different values for this omega p because this rho 0 is different. So it all depends on rho 0. The others just universal constants. M is the electron mass, and 4 pi e squared is just the universal constant. So different metals shows different plasma oscillation frequency because they have different electron density. Okay, and that's all. And we could indeed consider electrons are moving and dancing together with the same frequency. Okay, remember this omega p is the oscillation frequency for every electron, and not a particular electron, but everybody. Okay, so this is the key, that this is the frequency for all electrons, not just one, meaning everybody is dancing at the same frequency. And this phenomenon is called the plasma oscillation, and it is the purely quantum mechanical phenomena because we will see in just a moment that there is no such a phenomena in the classical electrodynamics. Okay, so very important remark. So when we derive such a plasma oscillations, do we apply a magnetic field? Is there a magnetic field or electric field when we perform such a calculation, a double commutator or Hamiltonian? Is there or is there not external magnetic field or electric field here? Tell me, yes or no. Is there a magnetic field or electric field applied here? No. What we have is just a free electron connecting energy plus the Coulomb potential, remember, right? And yet, they have this dancing together, that kind of phenomena, which means that this phenomena is purely quantum mechanically driven. Okay? We don't need to apply the external field to drive the system so that they will actually fluctuate like in the classical electrodynamics. So this differentiates this plasma oscillations of charged particles for classical EMM. So if this system is actually classical system, or just satisfying Maxwell equation plus Poisson equation, and we need to actually drive the system to the plasma region by external E field or B field, where this frequency is really high. So without the AC field, we cannot get to that plasma region if these charged particles are classical charges. Okay, but quantum mechanically, we don't need to apply any external field. And this phenomena, just happened at very low temperatures for a soup of electrons very close to the Fermi surface, and boom, they dance. And they dance collectively in the same frequency. Okay, so this is like a magic. So how come they could actually collaborate with one another and to dance collectively in the same frequency? Okay, so this is called quantum many-body phenomena. It's quantum because they obey quantum mechanics. It's many-body because they are made of many electrons near the Fermi surface. So it's not just a single electron phenomena. It's the many-body phenomena. And how many electrons are there? Well, you can estimate the rho 0, and you can count how many valence charge available for your material. It's the order of 10 to the number of electrons in the system is the order of 10 to the 23. Okay, it's that many electrons, they dance collectively because of Coulomb and because they carry quantum mechanical kinetic energy. So we will make some additional remarks, but this basic phenomena is really straightforward. Coulomb interacting electron gas, if we express this Hamiltonian in terms of the density operator rho in Q space, and we evaluate Heisenberg equation motion of the second order in time derivative, and this results simply just the consequence of this quantum many-body phenomena. And this phenomena has been observed experimentally many years ago, many decades ago, in say simple say metal film, say aluminum thin film, and if you strike this thin film by electron beam, and you can measure the outgoing electron energies and intensity as function of energy, and they show such a periodic modulations, and with the frequency precisely corresponding to the plasma oscillation frequency. So we will see that in just a moment. Good. So you could read the corresponding chapters in Flansburgh, in Kittel, and also David Pines. Okay, so let's take a short break. When we come back, we will make some additional remark. So remember, we made some approximation, right? The first term vanishes because the kinetic energy term is the order of q to the square, and we could check whether this approximation really holds. Okay, so let's take a short break. Any questions? Yeah.
这边通过空的每一方面来算出来的Plasma Oscillation frequency， 跟直接用classical dynamics 的方式可能测出来的这个会一样吗
？Well, classical electrodynamics, if you don't apply electric field or magnetic field, you don't have such a phenomenon. There's no counterpart in classical electrodynamics without external field. So you cannot talk about classical plasma oscillation without external field, because there's no such a thing. If you think about your classical electrodynamics, if you don't apply the field to the static charge distributions, will they dance? No. They satisfy the Poisson equation, but not Heisenberg equation motion as a density operator. So there is no such a thing in classical electrodynamics that you have such a plasma oscillation. That's right. So this is a quantum world. Welcome to the quantum world. This is a new phenomena. There's no such a thing in classical physics that you get such a plasma oscillation without external electric or magnetic field. Here, without any field, you get such oscillations. But you can see that this oscillation frequency is independent of h bar. You may guess whether this is a classical or a quantum phenomena. But remember, there's h bar here, h bar there. Okay? So the oscillation frequency is not a function of h bar, because this h bar just gets cancelled on both sides. So it doesn't necessarily imply that this is a classical phenomena if this quantity is independent of h bar. Okay? So even though this is some number independent of h bar, but this is quantum phenomena, purely quantum phenomena. Understand? Okay, good. I hope you really understand the physics. Okay, so mathematics is the secondary consideration, but you need to do the exercise once in your lifetime, but you need to understand the physics right now. So the physics is simple, that since these electrons are quantum particles, when they are in the neighborhood of the ions of some materials, say metals, they follow this Heisenberg equation motion. But for this Coulomb interacting electron system, we could really show that near the Fermi surface and low temperatures and long wavelengths limits, these low energy excitations are indeed this plasma oscillation physics. So let me just check whether this condition satisfy, namely this approximation. But before that, let me just make some notes. So plasma oscillation is a collective quantum phenomena. As I emphasized many times, this collective means all electrons move in the same manner. Okay? And the reason why they move is because they are quantum particles. It's called quantum many particle phenomena. So, as I mentioned, for classical electron gas, because the commutator between this classical Hamiltonian for electron gas and the electron density for classical particles, charged particles, vanishes. Because h bar is actually 0 in the classical limit. And therefore, without applying external field, this electron density will not oscillate, because the right-hand side of the equation, identically 0. So now you understand why there's no such a thing in classical electron gas, because the right-hand side of the equation is 0. Okay? So the Heisenberg equation motion for classical, say, electron density is really 0 on the right-hand side. Okay? But plasma oscillations for classical electron gas can occur, but it occurs only in external AC field. As I mentioned, if you apply the alternate electric or magnetic field to the classical electron gas, then they will oscillate. But it doesn't surprise me, because it just corresponds to the frequencies that of the driven fields, right? Okay, it doesn't surprise anybody. So number 3 is quantum plasma oscillation involve all electrons near the Fermi surface. So all electrons means this is a many-body phenomenon. Okay, so as I mentioned, so number 4, the wavelength is actually long when we perform such a Heisenberg equation motion, and this wavelength for the plasma oscillations is actually inversely proportional to this q, which is a momentum, right? And in a small momentum limit, when q goes 0, this 1 over q is large, so which corresponds to very long wavelengths of these fluctuations of its electron density in real space. Okay, so this is a very low energy because momentum q is really small, and long wavelengths. Okay, lambda is large. Okay, it's small density fluctuations. So let's just look at this approximations that we use. Remember, we assume that this approximation holds, and then we could drop this first kinetic energy term from the double commutator. Remember that. But let's just look back whether this inequality really reasonable. So, which means that this q has to be small enough, right? So q has to be smaller than what? Omega p over Vf, right? Where Vf is the Fermi velocity. Okay, but you know what this omega p is, right? So this is what? 4 pi e squared rho 0 over m square root, right? Okay, and what is Fermi velocity? Well, you could check your periodic table of these metals and check their Fermi energies and Fermi momentum, and then you could get this Fermi velocity. Okay, so if this ratio between this omega p and Vf is large enough compared to your momentum transfer, and that's fine. But can this condition be satisfied very easily? Well, of course, for most metals, these conditions can be satisfied. But of course, this is not infinity, right? This is some finite number. So this, in general, this q, the momentum transfer q, can go from, say, 0 to infinity, right? For example, this is the external momentum transfer. So then, this is a finite number. Okay, so if you sum over all possible momentum q, you must divide this summation into, say, two regions. One is the Q is less than QC, where QC is the ratio between these two. And when Q is larger than QC. So you must divide your summation into two parts. One is small q limit, and another is large q limit. Okay, so let's just look at the physics of these two regimes. For Q smaller than QC, and this condition is satisfied, so we are fine that this ratio is less than 1, so that what we have done here is fine, because this condition is satisfied. However, if Q is larger than QC, and this condition is violated, then we cannot get such a plasma oscillations. So the plasma oscillation phenomena only occurred in this region, okay, but not for large Q region. But what is the physics corresponding to this large Q limit region? Okay, so we have discussed that in the past. Anybody knows? When the momentum transfer is really large, what kind of excitations that we have? We have discussed that many, many times already. Just go back to your earlier notes and you will find the answer. So let me give you some hint. What is this? The correct name for that kind of excitation? What? What kind of excitation is this? If I draw another line, you will know the answer. So remember, we have a single electron hole pair excitation, right? So, but that kind of excitations is actually the eigenstate of the Hamiltonian only when this momentum transfer is large. Remember that. Okay? And this is precisely the physics happening when Q is much larger than QC, where the single electron hole pair excitations dominate. So single electron hole pair excitation. So there are many, many single electron hole pair excitations, but these excitations are uncorrelated, meaning each one of the electron hole pair excitations is independent of the other event. Okay, so this is not a collective excitation because you simply just excite single electron. But for small Q regime, this plasma oscillation phenomena is really a collective many-body effect because all electrons near the Fermi surface dance together in the same frequency. So they are related. They are correlated. But for this large momentum transfer region, those isolated electron hole pair excitations are a collection of uncorrelated single electron hole pair excitation. So let me just summarize this in a diagram over here. So suppose this is the axis of this momentum transfer Q, and this is QC, and for Q less than QC, we get plasma oscillations. For Q larger than QC, we get high energy single electron hole pair excitation. And therefore, in the high energy regime, the electron kinetic energy dominates, so we cannot ignore the kinetic energy part of the double commutator. Okay? But we can, of course, neglect that when Q is less than QC. So, of course, the calculations also obeyed the double commutator or Heisenberg equation motion, but the approximation is valid only when Q is less than QC here. This approximation. Okay, and as a result, this plasma oscillation becomes single electron hole pair excitation when this approximation fails, right? And you really need to include both the kinetic energy and potential energy. So now we really link this kind of an overshooting phenomenon that we qualitatively hand waving argued previously that electrons dance back and forth in time and also in space. So now we successfully show that the electron really dance in such a manner, and because they are quantum particles. But there is more physics when we understand these plasma oscillations. So the deeper understanding of this phenomena is the the connection between the Coulomb screening and plasma oscillations. So precisely because of these two regimes that we should divide when we perform this momentum sum. And in this plasma oscillation region, this the energy, the total energy of that electron C is actually lower than the Hartree-Fock energy. Okay, so we will perform a little bit estimations in the following, but let me just outline what we will do next time. Okay, so based on this kind of a division, we need to write down this Hamiltonian of this Coulomb interacting electron gas, especially the potential energy part, in terms of the large momentum transfer region and the term for the small momentum transfer limit. And we know very well that when momentum transfer is large, the Coulomb energy is actually sort of a short range, okay? Because this is the short range Coulomb interaction. Why? Because, as I mentioned, all the physics is dominated by the single electron hole pair excitations, and they are not correlated. They are not related to each other, right? As a result, these Coulomb interactions are really effectively not long-ranged, okay? So they don't really care about the interactions when the distance are too long. Of course, the really screening of the Coulomb potential has not been derived at this point, but qualitatively speaking, we understand that in this region, it is a single electron hole pair dominates, and therefore, the Coulomb interaction is effectively short-ranged, okay? Because this electron here doesn't care about the other electrons far away, okay? So they only care about this nearby. But for Q less than QC, we know this is a plasma oscillation region, and this is a collective motion, right? And therefore, effectively, this Coulomb interaction is actually a longer range. Okay, so this Coulomb potential can be long ranged. However, you will see next time that this form for Q less than QC, and also the solution that we found from this plasma oscillation frequencies tells us that electrons really do this kind of a harmonic oscillator-like motion, right? So in this region, even though we know that this Q goes zero limit, this Coulomb potential diverges. Remember that this V of Q is actually 4 pi E squared divided by Q squared, right? So if Q is much less than QC and Q goes zero limit, this term diverges. Remember that this is the problem of the Hartree-Fock, right? Okay, but this problem doesn't appear here because we know the solution already. Okay, the ground state of this system when Q less than QC is the plasma oscillation phenomena. Okay, and these plasma oscillations are the kind of a periodic motion of charge particles, which looks more or less the simple harmonic oscillators. And so we will see next time that from this kind of a connection, we know that the energy cannot diverge. So let's end our lecture today, right now, and we'll continue on this Wednesday.